So this is going to be a journey, say, on data-driven optimization in power system. It's going to be a little bit more on optimization and a small part on power system. I try to motivate it across disciplinary, and then I'm going to focus on power system. So any question, just ask. I'll try to make sure that everybody's on the same page at every slide. I'll use the Blackboard, depending on your questions and the ideas that we may discuss. And let's try to make it enjoyable for me and for you as well. Okay, so good. So what's going to be in here? I'm going to talk about time-varying optimization. I'm going to define it later on. I'm going to talk about optimal power flow problems that changes over time. And I'm going to talk about regularization as a technique that can be used on optimization problems to make them nicer. I'm going to talk about measurement feedback in optimization. I'll tell you a little bit more about it. So the motivation behind this is power grids or transportation networks are becoming bigger and bigger. So you are solving de facto like continental size optimization problems that changes over time because your wind generation changes, solar changes, or traffic changes over time. So you need to have solver or algorithms that can not only find the optimal operating point, but track it as it evolves over time of these continental size problems that oftentimes are not even convex. So that's basically the set. So to give you a little bit of handle on the recent work. So you can see, let's see if this works, great. So recent work that I'm going to present here or give some hints about it are the one with Emiliano at UC Boulder. For instance, this one is the one that you have either printed or on your computer or maybe read. I don't know who read this optimal power flow pursuit thing. Okay. Don't be shy. Yes, I read it as well. So, okay, a few, fine, doesn't matter. Good for you, great. You'll help me explain it, great. Or other works. You can find more information on our websites, meaning me and Emiliano's. I don't call myself we, so that's our, meaning me and Emiliano. And that's my email if you want to ask extra material or anything. Okay, so I usually don't put outline in presentations, but since this is a lecture, it's good that you know where you are and how much till the end. So I'll begin with some basics. So how many of you knows about convex optimization? So most everybody, good. So what's a convex function?
If you draw a line.
If I draw a line.
Yes, the convex function will always be, if you take two x's, right?
Two x's.
Yes, and then the f of x is, the line between those two f of x's will be always above the convex combination of those f of x will always be.
Sure, okay, good. Right.
Geometrically
speaking, fine. Okay, so I guess you have an understanding of what's a convex function, but if not, just ask. We'll review a little bit of gradient descent, Lagrangian formalism, and then we'll talk about a little bit more advanced topics. Basically, I'll focus on time-varying optimization, measurement feedback. The optimal power flow will come here. I'll spend a fair amount of time into that. We'll close with some results, and then I'll close back with some take-home messages. We will have then our hands-on session. So then I relax and you work. Good. So we started with a very general optimization problem in that form over there. I'm going to write it over here so that I have it. So we minimize over a convex function, which, what's your name? Kamal. Okay, define it very thoroughly, I'd say. So, okay, so we want to minimize So x in red is going to be my decision variable, right? So the decision variable will lie in a certain set. In this case, it's all Rn. So it's a good practice if you write down optimization problem to have always the decision variable below and where they lie. Okay, it's often very difficult in papers or in reports understand what you are optimizing on and what are your parameters. So it's a good practice to write them down so that you make everybody understand at the onset what are your optimization variables and what are your parameters. So over a certain cost function, okay, those it's convex. A convex function mean is defined over a convex set. And as he said, if you take 2 points of the convex function, the line between them lies always above the function of those. Okay, that defines upper bound on the function of those points. Minimize this subject to some convex constraint. Okay, this, for instance, is a convex constraint, or a linear. That's a convex constraint. Okay, this is a very general optimization problem. So imagine that you don't have constraints, so it's a complete unconstrained problem. Then the gradient method that is defined as you start at a certain point, you take the gradient, and you go down with the gradient, all right, which is defined like this. The nabla of x is the gradient of f at the point x k minus 1. So the gradient method is defined like this. Now, if f is strongly smooth, then you have certain convergence guarantees, and f is strongly convex and strongly smooth, then you have other convergence guarantee. What do I mean by that? Is that the gradient method will start at a certain point, x0, and then use that as a recursion. So you will compute the gradient and go down. Alpha is going to be your step size. Usually has to be greater than 0, of course. And you will have upper bounds on how you choose alpha to make your gradient convergent. So if f is strongly smooth, what I mean by strongly smooth is that I can have upper bounds on how the function changes. Okay, I'm going to write it like this. So if the function is differentiable and needs to be differentiable, but imagine that the function is doubly differentiable, that the f is strongly smooth means that the Hessian of the function, call it like this, at any point is upper bounded by a constant L, positive constant L, which we call the Lipschitz constant of the function. In practice, what it means is that you have your function that could be whatever, and at any point the function is bounded by a quadratic function, both above and below. So the function is sandwiched by two quadratic functions of was Hessian is, in this case, L, and this is minus L. Okay? That's what it means. So in that sense, we have a bound on how the function changes in space. Furthermore, if the function, so if that is the case, then the cost that you evaluate at your points of the gradient goes down as 1 over k. So that would be your convergence guarantee. And then if you use, say, a fast gradient method, Newton method, a Nesterov method, then you have convergence of the term of the type 1 over k squared, so faster. Now, if f is strongly convex and strongly smooth, strongly convex means now that you have if the function is double differentiable, then you have a lower bound on your Hessian. Okay? the function need not to be differentiable to be strongly convex, but if you have differentiability, that's what it meant. So if the function is strongly convex, so you have a bound on the curvature, in fact, it cannot be arbitrarily zero, arbitrarily small. So then, in that case, your gradient will converge Q-linearly, meaning that relationship is verified. So if the function is strongly convex, you have a unique minimizer, so I can write x star. And by each steps of the gradient, you're going to get closer and closer by that row. And now if you reiterate from 0 to k, then you will have a row at the power of k. Okay? Now you will have to choose alpha less than 2 divided by L for that to happen, but I don't explain why. Okay, that's very simple. That's the gradient. That's the basics of optimization 0.01. Okay? As I say, the word isn't always nice. What I mean is that the function may be not strongly convex or not strongly smooth. So those results will not apply in general. So what do you do in these cases? So in these cases, regularization can do a lot for you. So that's a main message in optimization, is that modeling your problem correctly it's part of your job and does a lot for you. If you model the problem not correctly, then your optimization methods or your solver can take a lot of time to solve a problem, while if you model it better, then you can have a solution faster. So the idea is, for instance, I'm gonna use this. Good. For instance, is the following. Imagine you have a function that is not differentiable, like the module, right? That does like this. Okay, this is the minimizer. So this function is terrible, right? It's not strongly smooth, it's not strongly convex. So you cannot even use the theory that you showed before to find the minimizer of that function, even though it's unique and it's convex. So if you have those terms in your cost function, usually it's not a good idea to treat them as they are, because your methods will be extremely slow. While it's a good idea in general to regularize them. So for instance, here one could think naively, I could instead using something that does like this. Okay, it's a quadratic approximation of the cost function. Okay, in this case, it may be strongly convex and strongly smooth, and then you have very fast algorithms to find the minimizer, which actually, if you do it correctly, happens to be exactly at the same point. Okay, so the idea is that don't be afraid to regularize the problems. There are ways to do it properly, or right. So, for instance, For instance, if the function is not smooth, you could use a Morrow's envelope, which is a way to smooth out the function in a structured way. So in fact, you're substituting your function with another optimization problem, which turns out to be, was derivative turns out to be smooth. So the derivative of this exists and is Lipschitz continuous. Now, it may be nuts to transform your cost function in another optimization problem that you need to solve, but in some cases, those optimization problems are easy to solve. Okay, you can have closed form solutions for those, or at least for the derivative, the gradient, right? So it's the only thing that you need. So it may be good to go for it. Another way could be to go for a plain vanilla regularization. For non-strongly convex function, I'm going to add a strongly convex term, like a quadratic term. Okay? And I can even add a little epsilon over here, saying that I can tune my regularization depending on how fast or how close I am to the optimum. Okay? You can imagine to have, at the beginning, when you don't have any idea of where you are, in solving an optimization problem, you can say, okay, I take the crudest regularization that I can possibly can, but it converges very quickly. And once that converges, then I can update my parameter, epsilon, and now I have a better one. And then I converge quickly because I know I start from a good point, and then I, etc., etc., etc. Understand? Right? That may be a better strategy than solving the original problem that was not regularized at all crazy points or whatever. Okay? So regularization can do a lot for you, and how you model the problems can do a lot for you. And especially when the cost function changes over time, the effect of a regularization, meaning I'm changing the optimum. Here I'm changing the optimum, or I'm changing the optimizer, are less of a problem, as we are going to see. Okay, the same thing can happen if you have constraint problems. Okay, if I go back to my optimization problem here that is magically reappearing. Now, thing goes pretty much the same. You introduce a Lagrangian function. The Lagrangian function put together x's, which are called primal variables, and mu's, which are dual variables. You weight the constraint by the dual variable. This is the transpose. Right? The x's now are living in Rn. Mu's are living in the positive orthant of Rq. I call it in this way. And so this is the Lagrangian function, and what you want to find, you transform a constrained optimization problem into an unconstrained one, where you are trying to find the saddle point of a Lagrangian. You're trying to find the minimum over x, and the maximum over mu of that function. And you can use, instead of the gradient, you can use a saddle point method. So the saddle point would work very similar. Instead of having the gradient of the function, you will have the gradient of the Lagrangian with respect to x, the primal, and which is work out this way. And the mu's will be then updated with the gradient of the Lagrangian respect to the dual variable. And now you have a plus because you're going to, it's a saddle point. You're maximizing over mu. And you need to project over the positive orthant because the mu lives in the positive orthant, but this is a very easy thing to do. So this is actually the end result. So this is also very basic. Who knew the saddle point method? Is known primal-dual method, Arrow-Hurwitz method. This method will solve the problem. Let's write it here. This method will solve the problem. You want to find the minimum over x that depends on Rn, and the maximum over mu that lives in Rq plus of your Lagrangian, which is x mu. Okay, it's a saddle point. This is actually equivalent under Slater condition. Doesn't matter. It's equivalent to the constraint optimization problem that I wrote over here, which means that once you find the optimizer pair, the optimal x star and mu star, you basically solved the constraint optimization at the top. Okay. Now similar things works in this case, which means, so this is again the saddle point, which means the convergence, it's linear under Slater conditions, which means that you need to have a point that verifies your constraints at inequality and not equality. Plus, you need strong convexity, as before, and concavity, and strong concavity, and strong smoothness. So the same setting as before, strongly convex, strongly smooth, but you need to have strong concavity of your Lagrangian as well. And for small step sizes that are written here. So what it means is that if I pack my primal and dual variable together, then the distance between this packed vector and the optimizer, in this primal dual optimizer, is going to shrink geometrically with this row. Okay? That means linear convergence, because this divided by this is actually a linear term that is less than 1, and so geometric progression, this goes faster and faster to 0. Okay? Good? So who can see the caveats or the killjoy or what the problem with this statement? So I'm saying I want strong convexity and strong concavity and strong smoothness. So you can imagine strong convexity as being your function being lower bounded by a parabola, a quadratic function of a certain a certain Hessian. Okay, so who can see a possible? Yes? If the constraint is linear.
It's not strongly monotone.
If the constraint is linear, if f is strongly convex, the function, the Lagrangian is still strongly convex in x. But what is linear, and I cannot change it? The linear term is actually mu. Mu enters linearly, right? Is the function strongly concave? No. Good. Great. So in general, the plain vanilla saddle point method will not converge linearly because the dual variable enters linearly, and there is no way I can upper bound it by a quadratic, right? So it's not strongly concave in that sense. So this results will not hold in general for saddle point methods. However, I could regularize it. As I say. I can add a term in x. If f is not strongly convex, I can add it. If f is strongly convex, this term is not needed. But I put it here as to be the most general possible. And then I can add a term that depends on the dual variable. In this case, it's minus because I want to be strongly concave. I'm maximizing over a minus quadratic function, right? So in this case, now the function is strongly concave and strongly convex. So I can retain back the linear convergence. Okay, so what I'm going to put myself here. What does extra term imply? I let you think for a bit. So the idea to push it a little bit more, the idea is that instead of solving this problem over here, you're solving a problem which is the same, okay, minimizing, maximizing, of a Lagrangian, which is x mu plus epsilon square minus mu, minus mu is mu square divided by 2. Okay, so in general, the optimizers, so the point that will minimize and maximize this function will be different from the one above, right? Those two are two different cost functions, unless you are specifically lucky or you do things very carefully. The results here will be different from here. Okay, the real idea behind it is that if you plot convergence, here we say error, whatever that be, and this is, I say, time, whatever that be, and below error is good, high error is bad. So I can imagine that a method that is applied to the function above here, since I don't have linear convergence, whatever how I define it, will be pretty slow. Say it's going to go really slow, and then eventually it's going to go to touch my zero line, so this is zero error. Okay? While the idea is to use regularization is that I may fix those two, then I'm going to go very fast to a bound, and then I change them a little bit, and then I'm going to go very fast to a bound. Then I change them a little bit, I'm going to get very fast to a bound, very fast to a bound, and hopefully, depending on what is the acceptable error, I could stop much earlier than if I had chosen to go for the original problem. This gap is all that matters. Okay? Save time. Okay? So but it's very educational to see. So if you add this term over here, so this term over here, which is this term over there as well, what you're doing, in fact, you're trying to select smallest x. Okay, so you're adding a term that somehow reduces, penalizes high value of x. Okay, so you're adding a term that penalizes high value of x here. Okay? So if you're not careful, it means that all the decision variable will be 0 or very close to 0. Fine. If I know that, I'll be careful. Now, what it means adding a term that is over here now? This will not penalize x's in general. So what this term does to your problem? Ideas, suggestions? Yes, good.
I guess UX
Right. What's your name? Chris. That's a real good. That's a good answer. Yes, we relax your constraint. Why? Can you explain me why?
Can you use the microphone? The microphone.
Yes.
I'm not sure if I can explain it, but I guess if it's not that the correct value, then for incentive to actually satisfy the constraint.
Yeah, you can very simply, if you put this back to the original form, which is the one written over here, that term over there means that you have a term here that is proportional to. So instead of this, you will have, with this regularization term, you will transform it into this term, divided by, right? Divided by 2. Right? Because then you can put it, you can form the Lagrangian, and now the Lagrangian will have, how you form the Lagrangian is going to be the function plus the dual variable times the constraint, and now the constraint is going to be g of x minus this, and now this is what we're going to have. So since mu is always positive, this is always a positive term. In fact, you're basically relaxing the constraints. Instead of being less than 0, has to be less than a positive number. And if the positive number is big, then it means that your constraints are not holding it. Okay? So if one term is basically changing your optimizer, the other term is penalizing the constraints, basically relaxing the constraints. Okay, so if you know that, you can always tighten your constraint such that the regularization has little effect to your constraints. Okay? Good? All right, so I covered the basics. The basics were gradient method and primal-dual method with some regularization. Okay, and the take-home message is that if you do things correctly and you add or you change the cost function accordingly, you can achieve faster convergence to error bounds that you deem acceptable instead of waiting forever and let your computer run the whole net. Okay. And if you're writing your PhD thesis, you don't want to spend you don't want to wait your computer to finish the calculation.
Andrea, you can.
Yes. Sure, please. Oh, okay. No problem. You lost a lot? No problem. I can do it. Yeah, sure. That's great. Okay. Good. So, question. Christian.
Yeah, I was just wondering if are you actually guaranteed that if you don't do the regularization, are you guaranteed that the problem will converge with this saddle point method eventually, in a million years, or is it not guaranteed at all? Or?
It's a good question. We'll see that in the exercises. Now it's a very open research question, despite being a very long known method. In some cases, it will converge. If you don't have strong concavity, it's harder to make it converging. In general, it's an open research question. There are conditions for which this is converging. In general, maybe not converging. Or you cannot prove linear convergence. Maybe it converges in a different way. Yes. Right. Good. Yeah, good. So, any other questions? Okay. So then I assume everything is understood. Let's move on. So I'm going to make it a little bit more complicated by now changing the problem in the sense that I am parameterizing the problem over the time. Okay, so what you really want now is to find an optimizer. So imagine that you have the optimizer is unique to fix the ideas, which means it's at least the function is strictly convex. So we want now the function changes over time. Why? Because the data are changing, the wind is changing, traffic conditions is changing, etc. And the same happens for the constraints. Maybe some constraints change for you. Some roads are blocked, or some generators need more power or less. So those is changing. Okay, so what you really want to do is try to find algorithms that can find and track the solution trajectory. So now you will have a trajectory. Why? Because for each time you can find an optimizer, and that will change over time. So you will want to find and track this trajectory while it evolves in time. Good. A very, say, naive way to do that, especially if the function is simple or small, is to sample the problem at every time instances that you want and solve the problem exactly. Okay, you can apply, say, gradient method exactly at every point. So you let it run at convergence at any given time steps that you want. However, this batch mode, so-called batch mode, doesn't work when you look at very large-scale problems where you cannot simply wait for the gradient to finish, or when you want the solutions very fast, because, for instance, you want to apply to a very high rate, a very high frequency. So you need solutions, or you need approximate solution fast, and in time you want to refine them such that in the end you're going to track the optimizer trajectory. So what I mean is that in many cases you cannot afford computationally to run your optimizer at optimality, your method at optimality. You just have to be content with approximate optimizers. So how we can set up online algorithms that track solution trajectories? So that's a big question. So again, let's now define a gradient method that is online, which is the following. It's you start at certain x0, doesn't matter where, and at every point in time you are gonna go down with the gradient of the function evaluated at that specific point in time. So my case are instances at which I'm sampling the function, and now I have a sequence of time invariant problems, and on each time steps I'm taking one step or a few. Let's focus on one step of the gradient. Okay? And then the function changes and I take another step of the gradient, and then the function changes and I take another step of the gradient. Okay? This is online, very, say, straightforward application of the gradient to online changing function. No constraint variation. Okay? Again, coming back, if it's strongly convex and strongly smooth, as we said before, and now what does it mean? This the optimizers are not changing arbitrarily fast. Okay, so I'm not jumping around. There is a trajectory and I'm following it, and this is bounded by a certain, say, variation. Then what I have is this error bound, which says that every time tk, then the error that my sequence commits with respect to the optimizer at that specific time will be bounded by something that depends on how how the error at the previous step was with respect to the previous optimizer, plus a certain error that depends on how the optimizer changes in time. Okay? So I introducing an error, fine, but that depends on how the function changes. If the function doesn't change, so the optimizer is always the same, then this part goes to 0, and I get back the solution I had before. Okay, so can we work out the convergence of this, and why I'm saying that the convergence, it's around an error ball of size of O delta. So can we work down? So who can help me solving these equations and looking at the asymptotical error? Please, one at a time. So fine, okay, good. So proof. So let's call EK as the error that you see over here. That's less or equal than rho, the error that you see at the previous step, plus rho, a constant term, right? So I can go in time back. So this is going to be rho k 0 plus, so let's do one step at a time so that you all see that. So this is going to be this, k minus 2 plus So I'm substituting here, right? So it's going to be rho. So let's do it even better. Rho times rho plus rho delta plus rho delta, okay? Which is nothing else than rho squared e k minus 2 plus rho squared delta plus rho delta, okay? And if you go till the end of the beginning of time, this is going to be something like rho I delta, and this is going to be k, I guess. Something like this. Okay, this is going to be most likely 1. Okay, modulo indices. Okay, this is geometric rates. This is a geometric, is the sum of a geometric series, which I believe, I hope for you, you learned into high school. How to do now, I want to have the lim sup of k goes to infinity of that expression over here. So the error at k is going to be, this term goes to 0 because rho is less than 1. And this term is going to be 1 over 1 minus rho times rho delta. Okay, and this is actually proportional. That's what it means. This is proportional to delta. Again, no. All right. Okay, so what I mean is that fine, now that we have a very simple method, it's a gradient method, it's just a transposition of the gradient method that we had, good. And that converges, good. In which sense? It converges linearly with convergence rate rho, good. Where it converges, it doesn't converge to 0, it converges somewhere in a ball of size rho, size delta, right? So if, good. So this will be your asymptotical error. So instead of going to 0, it goes to a ball of the error. So it wanders around, so geometrically or pictorially. You start somewhere over here. This is the optimizer trajectory, how it evolves over time. You start over here, and then eventually you're going to go around the ball of size that guy over here. Okay? Big picture. So, fine. I don't want to spoil your afternoon with too much proofs, but in general, not the most complicated one, but the simple ones are nice in a way that they are very educational, in the way that when you do them at least once, you know them, you try to understand why certain assumptions are made and where the errors come from and how you can do to better them, or maybe adding some regularizations or others. Okay, so fine. This is a plain vanilla online gradient method. Plenty of works. Okay, if you are interested in this line of work, plenty of works. This is what is called correction only, in the sense that you observe the function and you correct your current estimates of decision variable based on the current function. But you have also prediction error type of methods where you predict how the function would change in time, and then you correct based on the predictions that you made, and etc. If you're interested, this is one reference. I'm a bit self-referencing here, but there are many, so have a look. Good. The constraint case will work very similar with a doubly regularized Lagrangian or double smoothing. So I write it over here. Oh no, okay, this is something else. Okay, fine. That's fine. I don't want to look at that. So it will work the same, but with a primal dual instead. So instead of having, so now I have a cost function here that and a constraint that translates into a Lagrangian that depends over time, G, okay? And now I'm taking, what I'm taking is that one step of the saddle point method for a timestamp, okay? I'm sampling the function. I'm sampling, in fact, the gradients of the Lagrangian in respect to x and mu, and I'm doing one step of that, right? So what I do is, in fact, I will do xk is going to be xk minus 1 minus alpha, the gradient of the Lagrangian respect to at k minus 1, mu k minus 1, tk. Okay, and the same thing I'm going to do for, I'm projecting over the positive orthant of mu k minus 1 plus, now it's plus because I'm going up, of the same mu k minus 1, mu k minus 1, tk. All right, so that's it. That's the idea. Now, I'm showing you an example, trying to push for the regularization. So now this is a static case. The static case is for eta equal to 0. Now, it's not very important what's eta. You will discover it in the exercise section. So fine. So, and this is convergence. Whatever metric I'm using, it's not very important. And this is the time index, so the number of iterations I'm running. This is a static case, so the one that we have seen in the first part of the lecture. I am with blue is actually the case where I don't add any regularization. In this case, the function is nicer. So in fact, I have pretty nice convergence, okay, even if I don't add regularization. If I add regularization, no magic here. I'm converging. In this case, pretty much the same because the function is pretty nice, but I'm converging to a bound. Okay? So in this case, nobody really would like to go for a regularized Lagrangian because the original method already converges. Good, very good. Now, however, if I now put some variability in time, whatever that means, you will discover it again in the exercise. If I put some variability in time, I will have in green the one that is not regularized, and in red the one that is regularized. Now, both of them are basically the same. Okay, both regularized and unregularized converge to the same point that changes over time. Okay, it's a ball, as I explain it over here. It's a ball that depends on how the function changes, how the optimizer changes over time. All right, so what is the take-home message here? The take-home message is that although regularization, even a plain vanilla regularization that do not changes over time, that you don't tweak, okay? You're not restarting and tweaking, even that one. Even for a function that is very nice, okay? You wouldn't go for it in a static case, but for a dynamic case, things changes, okay? Maybe it's better for you to do things that you wouldn't do in a static scenario, not to mention when the function is not so nice. But even if we focus on this case, it means that the error you commit for the regularization may be totally justified if at the end of the day you're committing an extra error due to the time variation. And on the good side, why would you go for regularization here? Is that in the good side now you know you're engineering those terms ML. So you're your step sizes can be tuned. You can make your step size bigger. You can have a better convergence proof or guarantees even though the result at the end of the day with the regularization and not is the same. So that's a very strong advocacy of going for regularization. Good. You learn more on this on your exercises. Good. And now, all right. So I'm going to move on to something extra. Maybe it's a good term to pause for 2 minutes. I'm going to ask you if you have any questions. Take a deep breath. I don't have all the answers, so it's good to ask questions. Good.
So in all of this, we are assuming that every time step, the problem is strictly feasible.
Yes.
Okay, so that's a necessity.
Yes.
And how can we ensure without solving that it will be, without knowing the data, how it changes over time?
That's a good question. Yes, that's a good question. Yes. So if your constraints are changing over time, then it's a little bit more complicated to ensure that you'll always be feasible. There is no good answer to that. I mean, there are techniques that you can employ to say you can tighten your constraint. So for the untightened constraint set, you would be always feasible, or you can try to have make sure that your algorithm, your online algorithm, has a property is called persistent feasibility, meaning that at every point it generates something that can be implemented even at the next time. So it's a good question, good research question. Yeah. Questions? Yes, there. Troy. Good, great.
Without regularization?
Yes.
Orange is with regularization?
Yes, in the static case.
In the static case. So, as I see it, it is better without regularization in the static state.
Absolutely. In this case, the function is very nice. So,
but in the time varying case, they're the same.
Exactly.
So it is better without regularization.
So that's a good point. In this case, they are the same, right? But the two things. One, the conditions for convergence of the non-regularizer are stricter than the one for the regularized case. The convergence proof is way harder. What you can say is very limited, and you cannot tune your step size arbitrarily. On the other hand, if you go for regularization, then you have much more parameters to play with. You can tune the step size according to the regularization. You have much stronger guarantees, and you can say much more things in a much easier way. In this case, right, there are cases where the blue line will look awful because you cannot guarantee convergence. But in that case, it's a bit more difficult. Yeah. Yeah. That's right. What I'm saying is that the error that you commit can be justified by the fact that if it's small compared to the error of the time variation, you don't care. And if you get back a lot of things, maybe you should go for it. Yeah. Question? Yes. Please.
Is this method like oriented to find like a close solution, but when the time horizon is like very large? I mean, we can be sacrificing like accuracy in the short time, or maybe not ensuring that the system will collapse like in the short time, because the result goes for when time goes to infinity, right?
Well, you have fast convergence. You have linear convergence to a bound. Yeah. So fine. If I understand correctly your questions, means that at the beginning of time, you will have approximate solutions, and they may break the system, right? So in that case, if you're concerned about feasibility of your solutions, then you have to ensure that the solutions is feasible, maybe not optimal at any point in time. Mm-hmm. So for instance, if you have a set that is easy to project onto, so if you have bounds, for instance, the voltage has to be around maximum voltage and minimum voltage, right? You can project over those. You can have a projected gradient instead of a gradient, and that you ensure that the primal decision variable, it's always feasible with respect to those constraints, right? And eventually, it's going to go closer to solution trajectory in a ball. Yeah. Sometimes it's better to have approximate solution if you need them fast, rather than wait the eternity and have the optimal one. That will be useless, right? Yes? Over there. Good.
So I must admit that I don't really understand the problem statement. Okay. So x does not depend on time, does it?
So the cost function.
Can you show again the gradient descent
Sure.
that you have for this, please? So you're not double using the index k, are you?
So the cost function is parameterized over time. Okay. What it means is that, let's fix the ideas here. So for instance, you have a least square problem. Okay, that depends on data. Okay, so you want to minimize over x of 1 over alpha, 1 over half x minus b, that now depends over time. Okay, this is streaming of data, information stream. And now I want to find the x that minimize this at every time steps. Okay, so for each t greater than 0, which means at a given time tk, I want to find the corresponding x star k. Okay, so if I sample this problem at instances tk with k equals, say, 1, etc., 2, etc., then I have a sequence of time invariant problems x minus b at time tk. Okay, this is sampling. Okay. And what I want to find is actually the optimizer of this problem. So the optimizer at time tk, which I say it's the optimizer time tk. Okay. And I want to find it for each tk. Now, if tk, so the sampling period of this sampling is small enough, maybe I can't find it exactly because I don't have time to run my first order method or interior point method, whatever. So instead, I'm trying to, I'm trying to set up a sequence of approximate optimizers that eventually converge around a ball of the true solution trajectory. Exactly. And the argmin is a function of time. Exactly. It's a parametric value. Yes. Yeah. Good. Now, okay, take a deep breath. I know it's not easy to digest. There are many things together. You have the slides. You can go over it. You can ask questions. You have my email. Think a bit before sending me an email, but sure, I mean, you can ask me questions. And right. Okay, so any other questions? No. So I have one question. What are we doing this for? Hold on. I'll give you an example from power system. So the last bit before we dig into power systems, I want to give a general picture of what's called cyber-physical systems and what's a key challenge with them and how we can overcome that in some ways. So in general, who knows what are cyber-physical systems? If you don't ask it to define it, okay, yeah, it's pretty complicated, right? So Wikipedia is something, your professor is something else. So in my interpretation, cyber-physical systems is you're optimizing. So you have two layers. One is the electrical engineering mathematics layer, which is you're trying to optimize something. And then you have a physical layer, which is basically governed by the physics laws. That's my interpretation. Okay? What it means is that in the end of the day, you have an optimization problem that depends on, so the decision variable here are x's and y's, different dimension. The cost function will depend over time, but forget about time, for instance. It's just a cost function of x and y. Okay, fine. X will be asked to lie in a certain set, and this is typically a convex set that the engineers put together. Okay, the engineers decide the sets. Usually are easy sets. Can be pretty complicated, but usually are easy because you want to solve the problem. So engineers are smart and put it very nicely. So maybe it's a box constraint. Say the voltage cannot go above a certain threshold, below a certain threshold, etc. Okay, this is engineering constraints. Usually are convex because we design them. Unless we okay, fine. On the other hand, there is the physics of the problem. You can't design it. That's the nature that designed it for you. And it's usually non-convex. So if you take the power-voltage relationship, is going to be a non-convex relationship. I don't know, if you look at fluid dynamics, this is going to be how the Navier-Stokes equations is non-linear, non-convex here. Or other things, if you're looking at whatever. Usually the physics here is non-convex because this relationship is not linear. Okay? For this to be convex, this relationship has to be linear. And it doesn't happen very often. Okay? So in many cyber-physical systems, as the structure, also the optimal power flow equation as the structure. There is something that is the physics that is non-linear. There is something that is convex, which is the engineering part. And the cost function is also nice because you design it. Okay, in these particular cases, one can say, can we linearize? So plain approach would be, okay, the problem is very difficult. Andrea told me that if I model it correctly, I can get fast convergence. So to model it correctly means I either get rid of this or I linearize these constraints. And then I successively linearize it at different operating points. And that's the idea behind, say, I don't know, sequential quadratic programming or something on that line, sequential convex programming. You are linearizing the constraints that are not linear here, making the problem convex, and then you're continuously re-linearizing at every operating point. So what I mean by linearize, and in this case, I want you to look at a single linearization. So I want to substitute, instead of this pretty complicated y equal mx, which we can think of it, so just to fix the idea. Imagine so instead of y equal to mx, which is maybe too abstract, you can imagine y is equal to, I don't know, cosine of x. Okay? That's a nonlinear relationship. I don't know of any system that has this structure, but who knows. So you want to linearize it so that the problem that you end up with is convex, and you know you have all the guarantees that you want, and you know how the convergence goes, etc. However, you are basically sacrificing the physics. Okay, you're linearizing once you find the best model that basically around your working condition point represent the physics the best you can with some error that you can bound. Okay, you're sacrificing the physics. Your decision variable may be not feasible for your physics, good, but you can solve it at optimality and you're happy with it. There are ways to do that, fine. Or the concept I want to get across to you today is a different one, is instead of linearizing it once, is to use feedback from the system. Okay, so we are talking about a physical system. In practice, you could apply the x, the decision variable, to your system and measure the y. Okay, this is physics. This is something that the system can solve. Right? If you apply certain voltages, it's going to give you currents if you measure them somewhere, or powers. So if you have a way to incorporate feedback in the form of measurements of how the decision variable x affect your system, if you have a way, then maybe it's a good thing for you, because then you recover feasibility here. You recover feasibility. Okay, so let's do one step at a time. So what you would like to solve in the full generality, it's over here. You have, in this case, I'm forming the Lagrangian, and I'm using a primal-dual method. So what I have is xk is going to be the projected gradient. So here this is xk minus 1. Sorry for the typo. Xk minus 1 minus alpha, the gradient of f evaluated there, minus alpha. That's pretty complicated expression to say you want to do the gradient of x of this over here that depends on y. In the end, you can substitute instead of y, m of x, and then this will come out about. So this will be what you should do, but you know that the problem is non-convex, so you don't really want to do it because you can end up in local minima, you don't have guarantees, pretty nasty. You don't want to do that. So if you were to linearize it, once, this is what you would end up doing it. So there is a transpose, and then there is this guy over here. And now it depends only on x. You will have to take the derivative of h respect to y, fine. But that's what I call the field forward, in the sense that you linearize it once, and there is no going back. This is going to be what you're going to do for the end of the time. But as I said, this ensure convergence, because now it's a convex problem. Ensure convergence to a point that is not necessarily your optimal, but what I care more is that this point does not respect the physics of your problem. Okay. If I use feedback instead, this is what I would be doing. Is instead I'm using a hybrid of the two. Now I'm applying this xk minus 1. Okay, I get xk minus 1. I apply it to the system. The system gives me back y. I don't need it to put it back. I don't need this anymore because the system gives me back that. So I can actually plug it into the system already. Okay, so this is the derivative of y, of h, of y that I measure. And this is the A transpose, which is coming from the linearization. So I'm de facto correcting the linearization by a measurement of the system. And if you do things correctly, you have both convergence to an optimizer of this regularized problem and feasibility with respect to the physics. The feasibility comes from the measurement. You impose feasibility by measuring. So your system is already imposing feasibility of some of the variables, of course. Convergence comes from the fact that if you do things correctly, this is still or can be bound by a convex optimization problem. Of course, you're converging not to the optimum of the original problem, but to something that you can, guarantee it's optimal, feasible, whatever. Okay, so that's the broad perspective. We are using the systems to ensure feasibility of some of the variables via feedback. Okay, this is a lot to take in. It's not easy. So I put a very, I would say, almost trivial picture. So this is your favorite first-order algorithm. This gives out a certain decision variable, x, okay, and then is applied to some part of your system, and then you measure the effect somewhere else or at the same point, doesn't matter, and that goes inside the input. So this is the feedback that you get inside. In fact, this is a feedback that improves your algorithms by telling them, by basically correcting the error they are making by the linearization they're choosing. Okay, and yes, that's the motto is let the physics do the job for you, and that's actually turns out to be pretty important for power system, for instance. So if you're interested, and you can look at those research area from optimization control perspective. But I want to give you an example in power system, so I hope that we can fix the ideas for that. Okay, so now I'm going to break. I'm going to ask you if you have any question, and then we are going to dig in a little bit more on power system. So I guess a lot of questions come to your mind. Don't be shy. Okay. Questions? All right. Once again, let's see. Once again, you have a problem that is non-convex. Okay, you have a problem that is non-convex. Right, and why is not convex? It's not convex because the physics is not convex, and you can't do anything about it. So one idea is to go for linearizing the physics. The physics, once and for all, for instance, or it can be sequential. If you're linearizing once and for all, then the problem becomes convex. You know everything about it. You can use your favorite solver. You have guarantees, whatever, and you converge to a point, these x and y's, that are not optimal to the original problem, and they don't verify the physics. So those those voltages and currents, they don't verify the Kirchhoff's law, okay, or any other law. So it's pretty meaningless, okay. You want to solve a physical system, and then you end up with a solution that is not physical. Okay. On the other hand, you may want to On the other hand, you may want to use. So how you can patch it? How you can have an algorithm that would have a convex problem and solve it in some using the physics to get back solutions that are actually physically realizable. And one way to do that is to modify your convex algorithm. This is a gradient via feedback, so feedback, in the form of you're measuring the physics, you're measuring values because you're applying the decision variable to the system, and the system gives you back automatically because the system is governed by the physical equations that you put inside. It gives you back the y variable plus some noise, fine. We can deal with noise. And by doing that, if you do that correctly, then you end up with something that is measurement based or feedback based online optimization, for which you have guarantees that you're converging to a point that is not optimal for the original non-convex problem, fine. However, this point is feasible and verifies the physics, which is in fact everything that you care about. And if the linearization of your problem is good enough, then the difference between the solution that you have here to there is not too big that it makes a huge difference. And again, if the problem changes over time, that error it's completely manageable. Okay? It's a lot to take in. Question? Good. Yes. Microphone.
So if the non-convexities that you have
Yes.
affect your feasible region,
Yes.
is it possible that, how are you going to sense if you're driving your system in a point where you're reaching local infeasibilities due to the non-convexities? Because you're only getting the feedback from your system.
Yes.
But if the feasibility there is dependent just on y's.
Yeah, okay, that's a good point. Yes, that's a good point, right? So if you're right, if the y's have a constraint, I didn't put constraint on y, if you saw, right? So if now the constraints are also on y, that's more complicated, right? That's more complicated. You may want to dualize them. You may want to do something about it. You may want to rewrite it as a constraint on x instead. That's not so trivial to do. That's a good point. But I'll show something for the optimal power flow that we did in that regards. Yeah. Yes? Cool.
So you need to measure a variable, right?
That's correct.
Because how much does the measurement error matter then? Because your measurement could be wrong.
Right. Sure. Yes. I mean, if the measurements are way off, then there is no reason to do that. I mean, I am doing that knowing that the error I commit that enters in the system here is kind of bounded. You know it, and if it's too high, you change your sensors to have better measurements, or you have more measurements. I mean, this is something from the engineering perspective that you can deal with. If I give you a system that can guarantee convergence and stability and whatever you want, it's a pretty good price to pay. It's a reasonable price to pay to put better sensors in that sense, if I can, yeah. I mean, we have the old theory in that okay, how this enters and how does affect and what is the trade-off. That's fine, but that's not the question. Yes. Oh, good.
Y hat is
Yes.
doesn't have to be really mx, but maybe there can be some kind of noise or error. So could it be of some sense to use a simulation to have measurements?
Sure,
Instead of
you can put simulations instead. Yeah, if you have a simulated model, it can be a pretty complicated model. Yeah. It can be many things. I mean, I put it there. Where is that? I put it there as a system, and I have but it can be a black box, right? Something that you don't know anything about it, and then you want to have some and you measure it. For instance, it could be your personal satisfaction, right? So this gives me the personal satisfaction of individuals to, say, the temperature in their home, or the times at which you want to charge your vehicles, or the temperature of the water in your shower, okay? I apply certain decision variable, I don't know, 20 degrees for your shower, and I get a scream out of it, and then I'm gonna change it for, I don't know, 40 degrees, and I get another scream about it, so then I try to, you understand, I don't have to model it. If I have a system that can give it to me, then that's the whole point here. But it can be a physics, and then it's a non-convex, and that's the problem. Yes?
Pass it.
So I have a question about the time issue, actually.
Time.
Yes. So basically, if you have a black box or whatever that help you to make your question convex or whatever, how are you making sure that this delay will not make influence on your initial problem?
Yeah. Right. So if I change it a little bit, the questions, because I think it makes sense, the question would be, how can I make sure that the dynamics of your system will not destroy the convergence of your algorithm? Because now I have, the system has to converge to something that is a steady state value, right? It has an internal dynamics. And the optimization problem has an internal dynamics as well. Good. So in most cases, I'm working on a time scale separation principles. Okay, the dynamics at which I collect the data, I run the optimization problem is lower than the dynamics of the network I am controlling. Okay, if that would be the case. So for electrical systems, that I think it's the case. For people under the shower, maybe not. So I'll keep moving, and they will not be happy. But yeah, for electrical system, makes a lot of sense. The dynamics is faster than water, and I can have a separation of the scales approach. Yeah. So everybody understood these questions? I think it's pretty important in general that he asked whether the system, when I apply something, is going to go and the dynamics will affect basically this y, and if I'm too fast, it's not going to be a steady state, and I may render it infeasible by applying a new decision variable when the system has not converged yet. Okay. In general, if I use a separation of scale approach, that's not a problem, right? And in an electrical system, that's fine. Okay. So this is again, this is pretty crazy. It takes a bit to get in, and I guess you guys all are exhausted, as am I. So let's do something more fun. Let's look at something that you probably know better, that the optimal power flow. Okay. So, okay, I'm going to do some baby steps towards introducing the optimal power flow and showing how everything that I spoke about today was not just thrown in the wind as some repercussion in how we do things in, for instance, in electrical grids, smart grids. And hopefully I convince you that it can be applied to all the other things. But if you're interested in power flow, that's something to look at. Okay? So I don't want to go into the details of what's what. This is the example that is written over here. If you have any questions, I'm happy to go to the details. So the general setting, it's a feeder. It's a feeder here. This is a distribution feeder. You have the zero node, which is on the very right. I have my pointer, and then you have n big N different nodes, you will have, you collect the voltages and currents at different nodes. That's going to be the graph. This is your power, reactive and active power at the loads. Then you collect the voltages and the currents in one single vector. And on a subset, you have generation here. You will have power generation by, for instance, photovoltaic units or wind farms or others. Okay, this is a very general setting. You can look at all the details on the paper. Okay, I'm going to go through this now. So the idea, I'm formulating alternating current optimal power flow problem. You want to minimize a certain cost functions that depends. So what are the decision variable? The voltages, the currents, and the powers at the generators. Okay, and there is a cost function that depends on the power. There is a cost function that depends on the voltages. And why it's so is also explained in the paper. So you have Kirchhoff's laws on the network, and this is going to be a matrix that depends on your resistances and stuff from the network. So this is, this is at the 0 nodes, and that will be your current and voltages. Fine. These two will be the physics that you cannot do anything about, that basically puts together the voltages and the currents in this nonlinear form. And since now they are the Vi are actually your decision variables, this is the fact, this is the complicated variable. Okay? And these are the engineering constraints. The voltages has to be limited and the power has to be in some convex set. Okay? Pretty, I would say, standard, but if not, we can walk through it in the paper. So this is fine. This is on a sub-selection of nodes. This is on every node at this power, photovoltaic or wind farm. And this is also selection of nodes. Okay. So in fact, this is the problem. This physics that bothers us. So we collect the net power injected. So it's going to be, P is going to be the real part of S, and Q is going to be the imaginary part of S. And this rho is going to be the magnitude of the voltages. So this is Rn. Good. So we transform, we are now introducing a linearized model for the power flow relation. Instead of using this, I'm using a linearized version of the power flow relation, okay, that depends on this, it depends on powers, basically. P and Q are powers. Good. H, Q, A, J, B, R, B, and A are matrices and vectors that you define once, and that's it. And that's the relationship between the voltages and the magnitude of the voltages that is written over here. And this helps you writing the magnitude constraints on the voltages in a linear form. So this has to be greater than the V min, and this will be greater than the V max. And this is where I'm going to add the measurements, because I want to make sure that my voltages that depends on the powers are actually physical and they do not go below or above the limits I'm putting myself. Okay, so I'm linearizing these terms, and this helps me with the problem because now it becomes convex. Good. So in the end, the relaxed or linearized optimal power flow will be of the following form. So you're minimizing a cost function that depends on u. U are the new decision variables, are nothing else by the power, the P's and the Q's, the reactive and active power at the generators, this. F is the new cost function, which puts together both the voltage costs and the power costs in one single one. Okay, we have a linear relationship between the two, so we can go back and forth. And the constraints now are basically enforce the voltages regulations. That has to be less than Vmax and greater than Vmin at specified nodes. Okay, and then you have a set that says where the power has to lie. Okay, this is, again, you have the slides, you have the paper. This is not the main idea. Is that we can model optimal power flow in this way, where you have inequality constraints, you have constraints, convex constraints over here, which we believe are easy to project onto. And we are minimizing a cost function, which is convex on the decision variable. Okay? So, all right, so we have a function, we have a cost, we have constraints. We can do a regularized Lagrangian. So we can use a saddle point algorithm or a primal-dual algorithm over what? Over the decision variable and which are u, which are the primal variable, and the dual variable, which are the gammas and the mu's. The gammas and the mu's multiplies your g's, which are the, yeah. Sure. You want to have a break? Sure. Okay, good. It's a little bit anticlimactic. I stop here, fine. I'll be back in what, 5 minutes? So, okay, I'll try to wrap up in 10 minutes so that you can work and ask me more questions. Right, so what were we? Let me see. So, right, so we did a long journey to say a few things. So what we want to do now is to look at the optimal power flow and see how we can linearize the difficult bits and then incorporate measurements so that at the end of the day we are making sure that the solutions are feasible with respect to the physics. Okay? And that's actually making our solution better because it incorporates real dynamics from the physics. Okay? You can think of it as if you are only linearizing, it's like a feed-forward controller, something that is open loop, in fact, riding your bicycle only looking behind yourself. With and yeah, it's not a good, yeah. It's got a new. I'll think about a better example. But anyway, when you use feedback, you incorporate measurements from the real system, and that will make their solution better. Very holistic view. Anyway, so what we did was we had this nonlinear equations. We linearized them somehow. You trust me that this is the correct way to do it. And by doing that, linearizing that, you can linearize the constraints on the voltages, the minimal and the maximum. And then we will actually enforce, we'll substitute this by the actual measurement. Given a certain power, we will measure the voltages that it generates, and then we try to enforce this by that. And if you trust me, at the end of the day, you end up with a regularized, actually it's not regularized, a linearized optimal power flow problem that is looking awfully like this, but where the decision variable are the powers, and everything is convex because you linearized the nonlinear equations, and now you have only inequality constraints and some convex constraints for the power over here. Now this is suitable to use a saddle point method. Why? Because you have a function and some constraints. Okay. So we use the saddle point method where u are the primal variables and gammas and mu's are the dual variables that penalize the constraints over here. Okay, this is I don't want to go through the details again. This is a saddle point. The problem with that is not strongly concave in the dual variables, and we don't like that because we would like to have linear convergence. So why? Because we want to apply our theory of this time varying optimization, since the cost function will change over time and the constraints may too. So I apply this double smoothing. So I'm adding a term that depends on the primal variables, this mu, and I'm subtracting a terms that depends quadratically on the dual variables and epsilon. I know that this will change the optimizer and this will loosen the constraints. Okay, but if I do things correctly, that's not a big deal. And I can re-update this epsilon and mu in a way that eventually I'm solving the original problem, in fact. Fine. So the plain regularized optimization problem would be you solve for u's, how you're going down with the gradient of the Lagrangian, okay, evaluated at the point. You're going up with the dual variables of the constraints here, and the same over here. So you have two variables because you have two constraints, and this is a projected over your convex set. So that's done in certain nodes. This is done in a certain other nodes. This converges. So yeah, so let's look at here. So you start with a non-convex problem, you linearize it as we did. You end up with a convex problem, which we have regularized it to make it fast converging, actually linearly converging. And you know that this is actually converging to a point. You know everything is a convex problem. You know everything. But the problem is that your y, in this case your voltages, will be not physical because they will satisfy a linearized equation. So the constraints that you put there may be not satisfied with respect to the original constraints, which were nonlinear. Okay? So what you do is you apply feedback to it by applying the powers to the systems and get back the voltages. So you make sure that the voltages are actually now corresponding to the bounds you have. So you collect the voltages measurements at certain locations, and then you update the dual variables as follows. So instead of this guy over here, these were related to the voltages. Okay, this is actually the difference between the V mean and the real voltages. And this is this guy over here, and this is the difference between the real voltages and the maximum. So the gap between what you can physically allow to your systems. Okay, you want to be sure that this is actually the real thing and not some linearized surrogates that you invented. Okay, so this is very important. And make sure that your system it's feasible with respect to the constraints that you have. So you use feedback in that sense. Okay? And then you can update the set point, the power set points the same way. So you're going to do, now you have the mu's and gammas, and then you can update. So this will be a feed forward, something that does not take in consideration the real voltages, but only the linearized version. And this is something that push powers, get back voltages, and incorporated that knowledge in the system. So correct the linearization by feedback, by measurement feedback on the system. And that's much better. Why? Because you know exactly what's the gap between what is actually measured and what's actually allowed. While here, you don't, because this is only a linear system. Okay, it's a linear approximation. And, right. So this feedback is kind of the best of two worlds. In some sense, if you know how to the bounded difference between the two, you can still retain most of the guarantees that you had if you were solving the problem, the convex problem, and yet you enforce the physics. The system enforces the physics, so you're feasible with respect to the physics of your problem. Okay. And to nail it again, the idea was to solve the non-convex problem, but you don't have guarantees if you try to solve that. So we nail it down to something that we could solve and give guarantees, and yet being feasible with respect to these nonlinear equations. Okay, so I'm going to skip this. You can read it in the paper. The idea would be that we have convergence, fine, up to a bound, as I show over here. Now it's not very important. I'm going to show something like this. So we did some testing on real data. This is an example. There are many more. The idea would be that in this case, if you switch on the method that we have, in this case we have real load and solar data that changes pretty quickly. So you want to track the solution trajectory that makes sure that the magnitude voltages are within the bounds. And here we artificially then change the bounds pretty abruptly. And then you can see that actually the methods that we put together verifies those bounds so that you're feasible with respect to your physics and the bounds that you put. And then if you're interested, I advise you to look at the paper. There are more examples, optimality, constraint violation, etc. Good. Right. So we did a big detour, right, to say two things, to say three things, I think. So first, that if your problem changes over time, you should look at time-varying optimization algorithms. If you cannot afford to solve the problem exactly within the time it changes, it's better for you not to solve it exactly, but having approximate algorithm that eventually will actually track the solution trajectory within a ball. Okay, there is quite some literature around this, and it's related to online convex optimization from the machine learning communities. So those two are related. So if you are a fan of machine learning, this can be something that is related to it. Regularizing time-varying problem is not a bad idea, because anyway you're committing an error. So why not do an extra little error if it helps the convergence that you have? So regularizing is not a bad idea. Understanding how you can do it smartly and to help your specific problem, that's something that you should look at. Cyber physical systems have a structure which allows you to use feedback. So whenever you can, use it, exploit measurement from your system, and let the system solve the difficult part of your problem that you don't want to deal with it. Okay, there is theory in that respect as well. Okay, fine. If you have any extra questions, please do ask me now, later, email me at reasonable hours. On the slides that you have a lot of literature. You start that, and then you follow the thread. You will find many more. That's a very vibrant and rich research area. So have fun. Good. Now, I have hands-on lectures and hands-on exercises that have been posted somewhere. So you have them. So we should go over it. And you can use your favorite software to solve them. It's a bit of modeling, it's a little bit of coding. You can use your favorite solver to solve them, to code that. I use Python usually, but you can use MATLAB or whatever you want to use. Somebody in the break asked me about IBM research. If you are interested in IBM research, you can ask me offline more about it. I'm happy to discuss with you anything. Okay, good. Any question? I went a bit quickly on the last part, but I want you, the tools in the first part, to be clearer. Anyway, so question? Fine. Okay, so good luck with the exercises. Oh, no problem. That's fine. That's fine. Yeah, that's great. That's great. Actually, it's better than. I don't know. You know that.